All right, technology is tough for me. Okay, so last time we had talked about matrix elements. And so the idea here is, let's say you're given an operator, which we'll call A. A matrix element is just a bra, operator, ket, and that's a number, and that's a matrix element. Okay, so in particular, it's very often useful to talk about matrix elements in an ortho basis. So if we're given an orthonormal basis, that's a set of kets, phi sub j, where j is, let's say, 1 up to some number, that's the dimension of the Hilbert space. Then we can look at the matrix elements phi j, operator, phi k, and we can call those A sub jk, and these form a matrix. Okay, and so the idea is, if you have an operator A on this side, then there's a matrix representation, which you should think of as being really a separate thing, but they're in one-to-one correspondence. And the matrix representation has elements A11, A12, up to A1n, and A21, A22, up to A2n, etc., until you get down to the last row, which is A1n1 up to ANN. Okay, and they're not the same thing technically, but they're in one-to-one correspondence, which means if you're dealing with the operator A, it's oftentimes useful to write its matrix representation instead. And if you have the matrix representation in a complete ortho basis, then you've basically understood what your operator A is. Okay, and what does this matrix act on? If you've got a ket V, I have to figure out why my Apple Pencil keeps turning itself off. Okay, V is represented by a column vector, V1, V2 to Vn. And did it again. And then V, the bra, is equal to a row vector, V1 star, that's complex conjugate, V2 star, up to Vn star. Okay, so the important thing is to remember to take the complex conjugate when you're talking about the bra vector. So this leads to the concept of adjoints of vectors. Vectors means now a bra or a ket, and operators. Okay, so the adjoint of a ket, V, is just the corresponding bra, which we write like this. So they're not the same thing, but they're in correspondence with each other. Okay, and so you can take the adjoint by replacing the ket with the corresponding bra. And so it follows from that, that if I take a complex number multiplied by a ket, it has adjoint. That's the corresponding bra multiplied by the number A star, the complex conjugate. That follows from linearity and the other properties of the Hilbert space that we wrote down. Okay, now consider what happens if you have an operator A acting on a ket. So now this is an operator. So one way I can write this is I can just agree as a matter of notation to write this as AV within the ket. That literally means AV within the ket is the same thing as the A operator acting on V. And now the corresponding bra for that ket is equal to, just as a matter of notation, AV in bra notation. And I'm going to write this as the bra V times something we're going to call A dagger. Why am I allowed to write that? I'm allowed to write that because that's going to be a definition. This defines what I mean by A dagger, which is the adjoint of the operator A. Okay? So here's something that's nice, is given a product of operators, A with B, that really means act with B first, then act with A. That's the operation. Okay, that has adjoint, which I can write as AB in parentheses dagger, is equal to B dagger, A dagger. In other words, I act with A dagger, then I act with B dagger. So the order is reversed. And to prove this, the proof fortunately is a one-liner, or maybe a couple of lines. But suppose I look at the bra A, B, V, where V is some vector. Okay, by definition, this is V times AB dagger. But it's also true that I can write A times B times V is equal to A acting on BV, which again by definition is B times V with A dagger acting on it from the right. And now we can use that BV as a bra is equal to V times B dagger. Okay, and so putting those two things together, that says ABV is equal to V times B dagger, A dagger, which is what we wanted to check. Okay, so that proves that if you take the adjoint, it's the same thing as taking the adjoints of the individual operators and reversing the order. And this generalizes for any expression that means an equality, or maybe just a single expression that doesn't have any equality in it. If you want to take the adjoint of it, here's the recipe. Okay, so the first thing you do is you substitute every operator with its adjoint. So that's true. That's what you're going to do for all operators. You're going to substitute for any number in the expression. You're going to substitute, let's call it C. For every number, you're going to replace it by its complex conjugate. So that's true for all numbers. The third thing you do is you take every ket and change it to its corresponding bra and vice versa. So you substitute for every ket the corresponding, the corresponding bra. And the other way around, that's what the double arrow means. So for all kets and bras. And the fourth and last thing you need to do when you take an adjoint, and this is really necessary anyway, because otherwise the expression that you wrote down usually won't make sense, and that is reverse the order of everything. So if you started with a ket on the right, you're going to be writing down a bra on the left. And so for example, let me do an example. Of course, for the numbers, it doesn't matter where you put them. But for the kets and the bras and the operators, it does. So just for example, suppose you had an expression that looked like A times B times V times V W inner product. And let's say your expression claimed that that was equal to a constant C times another ket X. Okay, so both sides of the equation are a ket. But now if I take the adjoint on the left side, I start with W because I'm going to be writing things in the reverse order. I change W ket into a bra. The next thing I write down is the V bra, but I turn it into a ket. The next thing I write down is the V ket, but I turn it into a bra. The next thing I write down is the B operator, but I turn it into a B dagger. And then finally, I write a dagger. So that's the left-hand side. And on the right-hand side, I change my X ket into an X bra. And I change my number C into its complex conjugate. And it doesn't matter where I write the numbers. Okay, so this expression, the second expression I've written here, is the adjoint of the first expression. Okay, here's another example. So last time we talked about how you can form operators out of bras and kets. Let me, for variety, call it B. So I can make an operator called V ket, W bra. Okay, and that's an outer product. That's just the name of what that construction is. The outer product of a bra and a ket that makes it an operator. In fact, it's a linear operator. Basically, every operator we're ever going to talk about in this class is a linear operator. We just call them operators for short. Okay, but if I've defined it that way, I can ask, what's its adjoint? And so I just take the adjoint of both sides, and I get B dagger is equal to W. Notice W changed from a bra into a ket, and I wrote it in the reverse order with respect to V. Okay, so now with these four rules, we can take the adjoint of any expression. And if the first expression we started with was true, then so will be the adjoint expression. Okay, so some definitions. First of all, the definition of a Hermitian operator is going to be very important. So a Hermitian operator A is just one that satisfies that it's equal to its adjoint. And a lot of the operators we're going to be talking about are going to be Hermitian, but not all of them. Occasionally, we will talk about anti-Hermitian operators. And that satisfies the same thing, but with a minus sign. So an anti-Hermitian operator satisfies a dagger is equal to minus A. So here's an interesting fact, is that given any operator, A, not every operator is Hermitian or anti-Hermitian, but you can always write them as a sum of Hermitian and anti-Hermitian. So it can be written A is equal to A plus A dagger over 2 plus A minus A dagger over 2. So I've really not done anything there. I've just divided it into two parts because if I add up the right-hand side, I get back A. But now I can recognize that this is Hermitian. And this right here is anti-Hermitian.
Why is that Hermitian or anti-Hermitian?
Okay, so if I look at the thing here, that's Hermitian, I can take the Hermitian adjoint of it. The A turns into an A dagger. The A dagger turns into an A. And so it gives me back the same thing.
Oh,
And same thing here, the minus sign is going to guarantee that it's going to be anti-Hermitian. Okay, so one of the reasons this is important, we'll go into this in much more detail later, but recall that we've already claimed as one of our postulates that Hermitian operators are observables or correspond to observables. And observables are measurable things. Things that you can actually measure in a laboratory. So that's why that's going to be important later on. Okay, another important definition is going to be unitary operators. And so let me use U for that. A unitary operator satisfies that its adjoint is equal not to itself, but to its inverse. And so from that, it follows that if I have U dagger acting on U, I get the same thing as U acting on U dagger, namely the identity operator. So some useful things that I'm going to state about this without proving them is now let's say I form the matrix representation. Okay, then the following things are true. One is that the determinant of the matrix U that corresponds to a unitary operator has magnitude 1. So that also implies that the determinant of U itself is e to the I theta for some complex phase. Okay, so this is for some theta. I should say real theta, I guess, for some real theta. Another very useful thing about unitary operators is, let's say you have a unitary operator and you make its matrix representation, and you just look at the rows of the matrix. These are, it turns out, the components of an orthobasis. So just to understand why that has a chance of being true, if my space is n-dimensional, then my unitary matrix is going to be an n by n matrix. That means it has n rows, and the number of orthobasis elements is supposed to be n. So at least the counting there fits. Okay, and it's also true of the columns as well. So the columns of the matrix U are the components of a different orthobasis. Or at least in general, they're different. They may or may not be different. Okay, so that's one way to construct an orthobasis. Find a unitary operator and just look at its rows, and those will be the components, or look at its columns, either way. Okay, so that's unitary operators. A useful fact about them is that they preserve inner products. So what does that mean? let's suppose that I construct a ket V prime from a ket V by acting with a unitary operator. And then I have some other ket W, and I'm going to construct W prime by acting with the same unitary operator on a ket W. So the way to think about this, unitary operators you should think of as being like complex rotations. And so what we've done here is the same complex rotation on both of these kets. Okay, now let's look at the inner product of V prime and W prime. Okay, so from the previous line, I can write down what this is. This is W U dagger. The reason it's U dagger is because I took the adjoint of the line above it, W prime equals UW, times U times V. And then from the definition that it's unitary, that's the identity matrix. So I can just eliminate it. This is equal to WV. Okay, so the moral of the story is I do a unitary rotation or a complex rotation on both of my kets, and whatever their inner product was before, namely this, it's the same thing as afterwards, namely that. All right, as a corollary to this statement, let's say I do this with an orthobasis. So I have a set of kets phi j, and I'm supposing this is an orthobasis. Okay, then so will be the orthobasis kets that I get by doing a unitary rotation on them all. So this is where phi j prime is equal to the unitary operator acting on phi j. Of course, you have to do the same unitary operator acting on everything. It's no fair doing one unitary rotation on phi sub 1 and a different one on phi sub 2. You've got to do the same unitary rotation. But if you do this on an orthobasis, then this will also be an orthobasis. So the reason, of course, is because it preserves inner products. For an orthobasis, the inner products are all zeros and ones, depending on whether they're the same vector or not. And so if there's zeros or ones before, they will be zeros and ones afterwards. So that's what we just proved. Okay, and so a way of summarizing what we've learned about this is that unitary operators are the same thing as a change of orthobasis. So that's a very key concept that deserves to be highlighted. Okay. Now, suppose we transform all vectors by some fixed unitary operator. And this is any ket, not just a basis ket. Okay, so suppose we transform all vectors according to the rule that V is going to be replaced by the unitary operator acting on V for a fixed unitary U. So what I've done is I've done a transformation of my vectors. And this is called an active transformation. Okay, now let's look at what happens to matrix elements when we do that. So suppose I had a matrix element that was V bra, A operator, W ket. How will it transform? V, the bra is going to transform into V U dagger, remembering that I have to dagger things when I take the adjoint, times A, I'm not changing the operators A, and W is going to change into U times W. That's what happens under this transformation. And so what we can say is, oops, so we would get the same matrix elements or the same change in matrix elements if we kept the vectors fixed. The bras and the kets are fixed, and instead change the operators. So, but instead transform all operators. And the rule for how we transform the operators, we can read off this line above. What we should do is we should take each operator A and replace it by U dagger A U. And this way of looking at things is called passive transformations, because you haven't actually changed your vectors in this way of looking at it. You've changed your operators instead. But since the matrix elements are going to be what matters when we do some calculation, they're the numbers that we get out. It's nice to have two different ways of looking at it. The active way, where you change the vectors, and the passive way, where you leave the vectors alone and you change the operators. Okay, questions on that? All right, so another mathematical operation or tool that we're going to want is that of eigenvalue problems. And I'm very rarely going to write out the word eigenvalue because it's too long. Instead, I'll probably write e-value.
I'm sorry.
Go ahead.
Are you going to set any examples on any of these, or is this it?
Yeah, we'll do some examples in a bit before the end of today, I hope. Okay. So the eigenvalue problem is we often want to solve an equation of the following form. Okay, that I have some operator, and I'm going to call it omega for variety, acting on a vector v is equal to little omega that looks like a curly w, acting on v. So the idea is typically that you're given the operator. And what you want to solve for is the vector v and omega. So to be solved for is v, which is supposed to be non-null. If it was null, that would be too easy. Then it would automatically work. A non-null eigenvector, which I'm writing as e vector or e ket, and little omega is the corresponding eigenvalue or e value, which is a number. Okay, so we'll do an example of solving this in a bit, but first let's just rewrite it slightly. I can just move the right-hand side to the left-hand side and write it as capital omega the operator minus little omega the number times the identity operator, acting on v is equal to 0, which I remember is actually the null ket. Okay, so from this equation, I can tell that for a solution to exist, this operator capital omega minus little omega times I inversed must not exist. Okay, if that operator, the inverse of capital omega minus little omega I exists, then I can quit. I know there are no solutions. Okay, and the reason we know this is because otherwise, if it were true, then I could act with this inverse operator on both sides, and I would get my ket v is equal to the inverse operator acting on the null ket. And anything acting on the null ket is the null ket. Okay, but I've just contradicted myself because I promised you that v was not the null ket. Okay, and so this is a contradiction. So the inverse of this operator capital omega minus little omega I must not exist. And that implies from linear algebra that if you go to the matrix form for it, what you need is for the determinant of omega minus little omega times the identity, that has to equal 0 if you're going to have a solution. Otherwise, there will be no solution, and you're done. Okay, so this is a very important equation. This is called the characteristic equation for the operator omega, for the eigenvalue problem for the operator omega. So by the way, if it's an n by n matrix, this is a polynomial of degree n. If the Hilbert space has n dimensions. And the fundamental theorem of algebra tells you that it always has n complex solutions. Well, they might be complex. You might be lucky and they might be real. And we'll talk about in a little bit under what circumstances you can expect them to be real. So we can call them little omega with a label to distinguish which ones they are. Omega sub j, where j is 1 up to capital N. But some might be the same. The fundamental theorem of algebra allows that to happen. But if you count them with multiplicity, then there have to be n of them. So there's an algebraic equation you can solve. And once you know what they are, then you can solve the linear matrix equation that says capital omega the operator minus the now known eigenvalue omega sub j times the identity operator acting on v is equal to the null ket. Okay, so now at this point, we know everything on the left-hand side, except the ket v. And so now we're ready to solve for v. Okay, so that's the general thing is, first of all, you want to solve for the eigenvalues. And then for each one of the eigenvalues, you have to solve this equation for each one of the eigenvalues. Okay, once we've found the solution, it's usually done, although it's not strictly mandatory, to name that vector v after its eigenvalue. Okay, and so instead of writing v, I can write omega sub j. Now, if the omega sub j's, if there was more than one of them that was the same, then I might need another label to distinguish them, but we'll talk about that later. All right, so let's do some examples, and we'll start with super easy and then do a little harder one. Okay, so a good example is let's let the operator omega be the identity. That should be easy. Then the equation I'm trying to solve is identity operator acting on my eigenvector v is equal to my eigenvalue times v. Okay, but this is equal to v itself. And so from that, I learned that omega can only be 1. And so the statement is every non-null ket v is an eigenvector or eigenket with eigenvalue 1. All right, so that was super easy. Let's do another example of an operator that we have is the projection operator p sub x onto a ket x, which looks like this. Okay, and so then the equation that we're trying to solve is px acting on our eigenvector v is some number omega that we also need to find acting on v. So let's just write out what that says. If we put in from here, this I was missing, looks like an equal sign. Sorry about that. So if we put in this for here, then we're going to get x v inner product divided by x inner product times x the ket is equal to omega times v the ket. All right, so this right here, whatever it is just some complex number. And so what we need to be true is that v is some multiple of x. So v can be any complex number times x with eigenvalue omega equals 1. That will work. It's also true, there's another set of eigenvalues and eigenvectors we can write down. Any v such that its inner product with the x in the projection operator is 0 works, because then this number is just 0, and so omega is 0. Okay, with omega equals 0. So the eigenvalues of a projection operator are always 0 and 1. That's what we learned. All right, that was still too easy, so let's do a little harder example. I'm going to use the operator R sub alpha that I defined in the previous lecture, because we've already defined what it is. It had, remember, a matrix representation acting on 3 kets. The orthobasis kets were, we called them 1, 2, and 3. And so the matrix representation, R sub alpha, I'm going to write a double arrow, meaning this means the representation of the operator R sub alpha is given by this matrix. And it was cosine alpha, sine alpha 0, minus sine alpha, cosine alpha 0, 0, 0, 1. Okay, so that's the matrix representation. And the reason a matrix representation is a good idea is because then we can write down the characteristic equation, which is determinant of r sub alpha minus omega times I has to equal 0. And when you take that determinant, it amounts to the following equation: 1 minus omega times 1 minus 2. For cosine alpha, I'm just going to write c sub alpha omega plus omega squared. Okay, so c alpha is cosine alpha, and s sub alpha is going to be sine alpha from now on. Okay, so this is my characteristic equation, and now I need to solve it. Fortunately, one solution is obvious, that's omega equals 1. But the other solutions you can work out. I'm going to skip the algebra, but they are, so there's 1, and then from solving this quadratic equation, it turns out the eigenvalues are e to the I alpha and e to the minus I alpha. So these are the eigenvalues. Okay, and so now you can consider for each one of them in turn what the eigenvector is. So for the eigenvalue omega equals e to the I alpha, you ask what is the corresponding eigenvector. So we're doing all of this in the representation form. So we write down C alpha, S alpha 0, minus S alpha, C alpha 0, 0, 0, 1. And I'm going to write down here the components of the vector I'm trying to find, and I'm going to call them A1, A2, A3 as variables because I don't know what they are. But this is supposed to be equal to the eigenvalue, e to the I alpha, times A1, A2, A3. So the next step is to multiply out everything on the left-hand side to get a vector. This is C alpha A1 plus S alpha A2 minus S alpha A1 plus C alpha A2 and A3, just from doing the matrix multiplication. And so now if I look at what does that tell us, that tells us, first of all, looking at the last entry, that A3 is equal to e to the I alpha A3. And if alpha is non-zero, that means that A3 has to be 0. That's the only way. Then you can look at the first entry, which is C alpha A1 plus S alpha A2 on the left side is equal to C alpha A1 plus I S alpha A1. Right? Here I've expanded out my e to the I alpha. And that amounts to saying, because this cancels with that, that amounts to saying that A2 is I times A1. And then the middle entry of this is minus S alpha A1 plus C alpha A2 equals C alpha A2 plus I S alpha A2. And so now I can cancel this with that. And we get A2 is equal to I times A1, which is the same equation, which very often happens that you'll find out you get redundant equations when you try to solve these things. Okay, so now we've learned something about A1, A2, and A3. And so what we've learned is that the eigenvector for the eigenvalue omega equals e to the I alpha is some constant times 1 the ket plus I times 2 the ket. C here is just a number that I was calling A1, but I've just renamed it for no particular good reason. But this is true for an arbitrary constant c. And that's another thing, that's a very general lesson that we are learning from this example, is if you've got an eigenvector, you can multiply it by any complex constant you want. I should say arbitrary complex c, and you've still got an eigenvector with the same eigenvalue. So you can go through the same thing similarly. I'm not going to go through the algebra because we're very short on time. For the eigenvalue omega equals e to the minus I alpha, the corresponding eigenvector is an arbitrary constant c times 1 minus I times the ket 2. And for omega is 1, that was our third eigenvalue, the eigenvector is a constant c times the ket 3. Okay, so it's a good idea to go through this example. I wrote it out pretty quickly because of our problems at the beginning of class today with getting things to work. But for homework, you're going to get to do a couple of other examples of this, and so it's a very good thing to learn how to take eigenvalues and eigenvectors, or how to solve for them in simple situations like this. All right, so that's going to be it for today. Homework 1 is due today by, I guess I said, what did I say, midnight? And homework 2 is out on the website. And it's going to be due a week from today. All right, so that's it for today. Are there any questions?
Professor, I had some questions if you have time after class.
Okay, that's fine. All right, if not, then let me declare class over, and I will see you all on Friday.
Thanks. Have a good one.
Bye.
Have a good
See
one,
ya.
everyone. Bye.
Bye.
Bye, everyone.